Okay, so let's finish up with a quick recap of what we've learnt about curves. So we thought about a curve that went between 2 points A and B. Okay, and we said that if we have some origin, O, then there was some vector R that took us to a point on that curve. Okay, and this R was parameterized by some parameter T. Okay, so we have that R, which depends on parameter T, so these are the points on the curve, depends on some components X, Y of T and Z of T. Okay, with respect to some fixed coordinate system, X, Y, and Z, okay, with unit vectors I, J, and K. Okay, so these are components of the vector R. And T some parameter that changes, and as it changes, the point moves. So this is now R at T plus some infinitesimal dt. Okay, so we've moved along the curve. Okay, we thought about what this difference was. Okay, this change in R, we called it dr. And from that, we could write down a few things. So let's start with the length. So we saw that we had a line element, an element of length, this thing called ds. And we said this was the modulus of the vector dr, this vector of the points from this point to this point as we change t. Okay, and we said that this was dr by dt. dt, okay, which equals the magnitude of r prime of t dt, okay, where r prime of t is dr by dt, okay, so r prime of t is dr by dt, okay, so this is equal to x prime of t, y prime of t, z prime of t. Okay, and you can think of this r prime as being the derivative, so this is the derivative of the coordinate with respect to parameter t. If t is time, then you can think of this as the velocity vector, the magnitude of the velocity vector, dt. Okay. And we saw that the total length between points A and B, okay, we called it L before, I'm calling it S now, doesn't matter, it's just a number, it's a length, equals the integral of ds between A and B. Okay, and typically we only know our curve in terms of this parameter t, so we want to switch from ds to dt, and this is what we need. So it's the integral of the magnitude of r prime of t dt. Okay, so ds equals r prime of t dt, magnitude, and we're going between two limits now, ta and tb. Okay, so ta is the time, or the parameter t at which we're at point A, and tb is the value of the parameter t at which we're at point tb. Okay, so that was the length. Then we thought about these three vectors, the tangent, the normal, and the binormal. So let's think about the tangent first. This tangent vector, we called it t. Okay, and it was defined as dr by ds. Okay, so we can parameterize our curve in terms of t or in terms of s, and s just moves us along the curve, like it literally walks us along the curve. Okay, but generally, having a parameterization in terms of s, okay, we find it's quite difficult to get the curve parameterized in terms of this natural parameter, and typically we're just using the parameter t. Okay, so we want to convert from s to t. Okay, so again, ds is just this thing, r prime magnitude dt. So this is dr by r prime of t magnitude dt. Okay, and dr by dt is nothing other than r prime. So this is just r prime of t divided by the magnitude of r prime of t. Okay, or the velocity vector t divided by the magnitude of the velocity vector. Okay, and this tangent does what it says. It's the tangent to the curve at any point. Okay, so here maybe the tangent points like this. Here it points like this. Okay, and it follows the curve. Okay, and it points in the direction of the velocity, the instantaneous velocity. Okay, then we thought about what happens, how does this tangent change? Okay, so we thought about the normal vector. And the normal vector we define in terms of how the tangent vector changes, dt by ds. So the change in the tangent vector as you move along the curve. And we saw that this was equal to the curvature kappa times the normal vector. Okay. So the normal vector points towards the center of curvature. So as this tangent curves around this part of the curve, around here, then there's a center of curvature here. So the normal vector will be perpendicular to the tangent and point towards the center of curvature. Okay, so here n is the normal vector. Okay, and it's perpendicular to t. Okay, and kappa is a number. Okay, and we find it by just taking the magnitude of both sides. Okay, so the magnitude of n is 1, it's a unit vector. So kappa equals the magnitude of dt by ds. Okay, which we know we know our curve in terms of t, then again we write ds in terms of r prime dt. So this is 1 over the magnitude of r prime of t dt by dt magnitude. Okay, so if we're given a curve in terms of t, r of t, then this is how we find our curvature. Okay, we differentiate to find dr by dt, find its magnitude, and if we know our tangent vector in terms of t, then we just do this also. Fine, okay, then we thought about the binormal vector. Okay, and we define the binormal vector b as equaling the cross product of the tangent vector and the normal vector. Okay, so these three, t, n, and b, form a mutually orthogonal coordinate frame. So t crossed with n gives you b. Okay, and these are 90-degree angles. Okay, it's mutually orthogonal. And then we thought about, okay, so yes, so b is perpendicular to t and n. Okay, and we thought about how db by ds, so how b changed as we move along the curve. And we saw that this was a vector that points in the direction of n. And we gave this constant of proportionality, so the length of this vector, we called it minus tau. Okay, and let me make some things clear. So this is the curvature. And this is the torsion. Okay, and the curvature tells us how curvy a curve is. Okay, so a circle has curvature. Okay, and this has constant curvature, and this normal vector points towards the center. Whilst torsion tells us how this if you're thinking about a particle moving in time, how it lifts out of the plane. Okay, so this helix we see has non-zero torsion. Okay, so here B is non-constant. It changes as you move around the helix. Okay, but for a circle in the plane XY plane, so this is a circle in the XY plane, B points up and it's a unit vector and it points in the same direction as you go around the circle. So for a circle in the plane, we found that the torsion was 0. Okay, so for a planar curve, the torsion 0. If the curve lifts out of the plane, you get a non-zero torsion. So this torsion is a measure of kind of how it lifts out of the plane. All right, okay, and yes, just like we can find kappa by taking the magnitude of both sides, we can find the torsion by doing the same. So this is equal to the, minus of the, no, we take the magnitude, so that's fine. So we get the magnitude of dB by ds. Okay. So we've taken the magnitude of both sides. Okay, and typically we don't know the curve or B in terms of S, we know it in terms of T. So again, this becomes 1 over R prime of T dB by dt. Magnitude. Okay, so hopefully this gives you the idea that basically you can just start with this picture where you draw your curve and you draw this vector r and you change it a little and then everything else just kind of follows. Okay, so it's this ds that you need to remember. Okay, so if you can burn this ds equals r prime of t magnitude dt into your mind, then everything else just follows. Okay, and the last thing we didn't look at was, so we've got how the tangent vector changes, how the binormal vector changes. We don't have how the normal vector changes. So it turns out that there's a relationship that tells us what dn by ds is. Okay, and it's minus kappa tangent vector plus the torsion, the binormal vector. Okay, and I'll leave that as an exercise for you guys to work out. So you can think of if B equals T cross N, then this thing cyclically permutes. So we can write N equals B cross T. Okay, so N equals B cross T, and you just do dN by ds on this thing. So you've got d by ds of B cross T, and you just follow the steps that we went through to get dB by ds. All right, so hopefully that is helpful in kind of bringing everything together and helps you see that there's not actually that much to it. Okay, so it all stems from this ds is r prime of t magnitude dt, and everything follows. Okay.